at MIT, and he's one of my many colleagues in developing the current future of energy storage study that we've been working on at the MIT Energy Initiative that will be released in about a year. So Fikile, over to you.
All right. So hopefully everybody can see my slides. So good morning, everybody, at least morning for me. My name is Fikile Brushett. I'm a professor of chemical engineering, as Rob said, at Massachusetts Institute of Technology. And I'm going to pick up a little bit on what Professor Sadoway was talking about earlier, and some of the things that also Rob talked about a bit earlier, which is the differences in design for batteries for the grid as compared to the batteries that we've designed beforehand. I'm going to focus on redox flow batteries, and what I'll try to do is give you some sense as to what's going on in the redox flow battery space, what are the challenges that we face, and then I'm going to try to finish with maybe a few things that I believe to be grand challenges, although I wouldn't say that that would be an all-encompassing list. But the main focus of this talk is to try to help us get towards more quantitative approaches to improving battery performance. The way that you might think about this is that it's very easy to say we need a better battery or said battery is not good enough, but it becomes a little bit harder to identify what it is that you'd want to do to make that battery better. And so I think if we can get beyond saying qualitatively we need better batteries to what about the battery would you like to fix and how easy would it be to make that better to improve the performance, that allows us to become a little bit more actionable and deliberate in our approaches. So hopefully that theme will come through over the next 20 to 25 minutes or so. So I'll be a little bit longer than Professor Sadoway. So maybe it's a level set here, just to kind of bring us all back. One of the things that Rob mentioned when we got started was the idea that renewables were beginning to play a larger and larger fraction in the delivery of electrical power to the grid. Fossil generation is still a large part of this, but as renewables become a larger and larger fraction, we become more exposed to the intermittencies associated with those forms of electricity generation. And those intermittencies can be on the seconds to days and even seasonal length. And so we have to figure out ways with which to buffer that to enable delivery to the grid without uncompetitive costs. The way that's done typically now is through pumped hydroelectric storage. Basically, you have water at two different elevations, and you pump it uphill when you want to store energy, and when you want to provide energy to the grid, you let the water flow back downhill through some turbines, and you generate electricity. This is a very cheap form of electrical energy storage, and it's widely used. It's probably about 97 to 99% of energy storage on the grid today. Some of that has to do with the size of these installations, but some of it also has to do with the fact that it's been around since the 1930s and it's a very robust technology. I'm showing you here US pumped hydroelectric storage capacity from 2011. It's almost a decade old, but these things are large and they don't change that often given the size of the installation. And maybe we could zoom in to one of these installations. This is in Ludington, Michigan. And what you're looking at here is energy storage off of Lake Michigan, where you can see that on the bottom part where it says energy, that is Lake Michigan. And then there is a reservoir at a slightly higher elevation where water is pumped up and stored. And there's a little sort of gold box that I've drawn around there. That's the power associated with that station. So when you want to generate electricity, you let water flow from the upper reservoir to the lower reservoir. This can be a very inexpensive form of energy storage. As Rob mentioned, this is really the benchmark that we're going after. But the challenges I think are pretty obvious. It's really cheap because you have access to a large body of water, and really, what you need to do is build off of that. But say if we wanted to build it in other places where we didn't have access to this water, or if we didn't have elevation changes, this would be significantly more difficult. Also, these installations are massive, which means that it's a massive capital outlay to build something like this. Even if it's very cheap on the dollars per kilowatt hour, it's a lot of kilowatt hours that you need to build. But there's some features about this that we can take and be inspired by. One of the things that particularly inspires me is the fact that when we think about the scaling of power and energy here, the energy is dictated by the size of the reservoirs as well as the difference in height. The power is dictated by the size of the turbines, but you'll notice that they're decoupled, as in if I'd like to store more energy, I need a larger reservoir. And if I'd like more power, I just need to build out more turbines. But that flexibility is an attractive feature and something that we may want to go after. So what we're trying to do, say, is to think about, well, what would batteries need to look like if they were to be competitive with this pumped hydro storage? And how do we decouple from limitations in geography, as well as increase the energy density? What that allows us to do is to expand the portfolio, to go from enclosed batteries such as lithium-ion batteries and even lead-acid batteries as well, which play a role here, to systems that look a little bit more like the system all the way on the right-hand side of the slide, which is this flow battery, which has now energy storage materials dissolved in an electrolyte and pumped through a reactor. And of course, things in the middle, this hybrid metal flow system, such as zinc bromine type batteries. For the rest of this talk, I'm going to primarily focus on full flow batteries with two electrolytes with soluble redox active materials in there. It's not to say that the others won't play a role, but I'm going to focus pretty much on flow here. But the take-home message should be that any one of these technologies or these formats will play a role on the grid. It's the price and lifetime that's going to be paramount to grid energy storage. And as Professor Sadoway said, there's opportunities for lots of different batteries because of the diversity of needs on the grid. And so I'll talk a little bit about sort of the components of the flow battery to make sure that we can level set going forward. So this is a crude schematic of a flow battery. We'll start off with what's in the tanks. So for the blue and the red tanks here, typically you're going to have some sort of an active species. It could be a redox active metal salt. In this case, I'm showing you a vanadium salt with a supporting electrolyte and a solvent. So it could be something like sulfuric acid and water, or something more complicated than that. In order to store and release energy, these active species that are dissolved in the electrolyte are charged and discharged to alternately store energy in the battery and release energy from the battery. So this is how we cycle back and forth. Where that actually occurs is in the reactor, which is between these two tanks. This reactor, for those who are familiar, looks a whole lot like a fuel cell. It's got multiple layers, with the central component being the ion exchange membrane, which is sort of the clear thing in the stack that I'm showing on the top side of the slide. The ion exchange membrane, the purpose of it is to allow ions to transport between the two electrolytes, but at the same time to block the mixing of the active species. So we'd like to block the blue component and the red component, but allow the gold component to go through. So we want it to be selective to the species that are transporting through. Around that, we have now a flow field and a porous electrode. Well, the purpose of the flow field is to introduce the redox active electrolyte into the reactor. So you'll have it flow through the lighter blue channels, and then you'll notice that those lighter blue channels are dead-ended. This is the interdigitated flow field. Once it gets to a dead end, it has to hop up through this porous electrode, which I'm showing you on the right-hand side of the screen, excuse me. And within this porous electrode, you have a structure where we have convective flux through there, and then diffusive transport to the electrode surface where the electrochemical reactions take place. I'm showing an example. It looks under an SEM a little bit like what you'd imagine paper would look like, but it's carbonaceous and conductive. So the advantages of this architecture are that we're able to decouple power and energy scaling. So the energy is largely determined by the size of the tank. The power is determined by the size of the reactor. As compared to something like a lithium-ion battery where we have to have precision manufacturing, this should be simpler to manufacture and put together. It should have high durability and enable simplified maintenance. High durability in the sense that we can discharge and charge to complete cycles. It's much more robust to excursions. There's relatively low maintenance and mate tank or change out a reactor. So that makes your life a little bit easier when you're operating these types of systems. And there's location independence as compared to, say, the pumped hydro, where you'd be relying on geological architectures to make this cheap. But there's no free lunch. And the drawback for this is that redox flow batteries are largely suitable for energy-intensive grid storage applications or long-duration grid storage applications because you're dissolving an active species into the electrolyte, you necessarily have a lower energy density than, say, if you had a solid material pasted into an electrode. So consequently, because it has a lower energy density, you tend to need a larger footprint with which to put out the redox flow battery. And also there's a little bit more balance of plant that's involved in terms of managing the pumping of electrolyte around. And so this just gives you some sense as to what a redox flow battery looks like. But what we're trying to get after here on this slide is the potential to get to extremely low capital costs for long duration discharge applications. And so what I'm showing you here on the graph on the right-hand side is battery cost as a function of discharge duration, which is hours of discharge. It's a log plot, so we can see from 1 hour to 1 day, week, month, all the way out to a year. Lithium-ion batteries are a moving target. They're getting cheaper and cheaper as we improve manufacturing, come up with new chemistries, increase deployment. But largely, the thought is that the cost may end up on the order of $100 to $200 per kilowatt hour, which I think aligns with what Professor Sadoway said. Right now, redox flow batteries are a little bit more expensive. There's a number of different reasons for that, which we can go into in the Q&A. But there is a potential to get to significantly lower cost. And the reason is that as you get to longer discharge durations, you don't have to scale the reactor. You're simply scaling the tanks. And so ultimately, the cost will asymptotically approach the cost of what's in the tank. And so you can see for redox flow batteries, I'm showing VRB. I'll talk about that on the next slide. That's the vanadium redox flow battery, the current state of the art. While the current costs are a little bit higher, you can imagine that if we go to longer discharge durations, the cost will come down. We can also inspect improvements in performance over time. As these materials begin to scale out, we can get cheaper electrolytes, hopefully. We can get better performing reactors. That represents the blue line. But ultimately, we may need to go to different redox active components that are significantly cheaper than vanadium or maybe more abundant than vanadium. And so getting to the green line or maybe even the pink line ultimately may be where we want to go. So this just gives you some sort of a sense as to the scaling of battery costs and the why flow batteries may be a little bit more attractive for longer discharge durations, whereas for shorter discharge durations, the energy density and the cheapness associated with, say, something like an enclosed battery lithium ion may still play a really important role here. So this gives you some sense as to there's a portfolio of options available. So I mentioned this on the previous slide, the vanadium redox flow battery, the VRB. This is the state-of-the-art flow battery technology today. If you went out and looked for flow batteries and saw what was the most widely deployed, you're more than likely going to find the vanadium redox flow battery. This was developed in the 1980s by Maria Skylos-Kazakos in Australia. And there's been a lot of effort, especially in more recent years, to try to advance this technology. You'll notice that there are a number of companies that I've put on the bottom. If you don't see a company here that you know of, I apologize. I had a limited amount of time on the slide. So I'm showing you Vionics Energy, which is in Waltham, Massachusetts, Uni Energy, which is in Washington State, Sumitomo Electric in Japan, and Ronka Power in China. The reason people like the vanadium redox flow battery is that it takes advantage of the fact that vanadium has 4 stable oxidation states within the water window, right? And so you have 2 oxidation states on the lower potential side and 2 on the higher potential side. So on the low potential side of the battery, termed here the negative electrolyte or the negolite, you're cycling between a vanadium 2 and a vanadium 3 species. And on the positive side of the battery, you're cycling between a vanadium 4 and a vanadium 5 species, all of which are soluble in a dilute sulfuric acid solution. The advantages of this particular approach is if you have a single parent compound, it becomes a very forgiving system. So if you have any crossover through the ion selective membrane that separates the 2 electrolytes, it's possible to rebalance and remix the system to regain the capacity. If anything precipitates out, vanadium 5 tends to precipitate out at higher temperatures. You can redissolve it in the electrolyte by either switching the streams of flow or by relaxing the battery a little bit. And also it has a relatively high voltage as compared to other aqueous systems at it's about 1.3 volts. Most other aqueous systems are 1 volt or lower. This actually is helpful for power and energy density. I'll come back and talk about that a little bit later. But There are challenges. First, vanadium is an expensive active material, and it's also volatile. Most of the vanadium that we mine goes into steel manufacturing, and most of it is mined, in places like China, South Africa, Russia, other places like that. If I've forgotten some countries, please certainly let me know. But there are challenges with this particular market, especially because flow batteries are a very small part of what we use vanadium for. And so the price of this technology might vary depending upon changes in the steel market. And so if you looked at the price of, say, vanadium pentoxide over the last year, you'll notice that, or last few years, you'll notice it's jumped around quite a lot. The second is, of course, limited energy density. As I mentioned a bit earlier, because there's limited energy density, to get a lot of energy stored, you're going to need a relatively large footprint, which may preclude certain applications for this particular technology. And so because of this, people have started to look for other technologies, but it's a really important thing to remember that redox flow batteries are nascent. We don't make a lot of redox flow batteries. We haven't really, looked at it with the same amount of effort as we've looked at, say, lithium-ion battery technologies. And this is largely because grid applications are somewhat new. So much of what we've been thinking about on the grid is emerging or has recently emerged. And so a lot of these technologies remained laboratory curiosities for many years. And now we're trying to see if we can make them into technologies to enable the grid. This is an imperfect representation of interest in redox flow batteries. This publication list is a function of year. I simply went to Scopus and typed in a couple of keywords to try to see where interest was. But I think it is somewhat representative of what our thinking on flow batteries. You'll notice that starting in the 1970s, there was very little in the published literature. And only right around 2010 have things started to pick up in a big way. And this has to do, if you overlaid, say, the price of solar electricity, you'd see that solar electricity is coming down around the time that interest in flow batteries begin to pick up a lot, as we now begin to think a little bit more seriously about how we might store excess solar electricity or firm its delivery to the grid. Still, this interest dramatically dwarfs what we've looked at for other energy storage systems, and consequently, I think there's quite a lot that remains to be discovered, quite a lot that needs to be found. And maybe another way to think about it is in 2014, flow battery system cost exceeded $500 per kilowatt hour, and the DOE set forth a target of $150 per kilowatt hour that they thought we would need to hit in order for flow batteries to be broadly successful. That's more than 3 times the cost of the flow batteries in 2014. And so what this presents is an opportunity for transformational technology advancement through either the development of new redox chemistries or through improvements in reactor design. And the community has begun to respond to this. And so there are many pathways that people are considering for cheaper redox flow batteries, moving away from expensive transition metal salts such as vanadium to perhaps organics or polymers that might be based on more earth-abundant type materials, to move away from acidic aqueous solutions, worried about corrosion, worried about maybe some other forms of hazards associated with acids, to neutral pH type solutions, more alkaline solutions, or even non-aqueous solutions that may allow you to have higher energy density. Moving away from ion exchange membranes, particularly fluorinated ion exchange membranes, which are quite expensive, to more size selective separators that may be effective in concentrated electrolytes. And then also moving away from cell designs that are begged, borrowed, or stolen for more advanced electrochemical technologies, things like fuel cells, to thinking about redox flow battery specific designs. And so all of these approaches have merit, and all of these approaches, will yield very interesting science. But there is a question as to what success might look like, and whether there are combinations of these approaches that might yield a better battery and might yield a better battery more quickly. And so what we're very interested in is, what does success look like, and how do we need to trade off each of these improvements to understand how the better system would work? Another way to think about it is that I may not need the best active material if I have a really great membrane and a really great supporting electrolyte, or I may not need the best membrane if I have a great supporting electrolyte and great cell design. Really what it is you're trying to optimize the system to minimize the cost. And that may mean that you don't necessarily need the best set of materials. You need the best set of materials working together or in unison with one another. And so the approach that we've tried to take is techno-economic modeling. This is similar to what Professor Sadoway mentioned in terms of cost-informed discovery. And the idea is to essentially say, can we connect materials properties to system targets? So if we have a desired system cost and a performance in mind, can we back calculate and say, well, what materials properties, what cost parameters, and what component performances would be needed in order for us to meet this particular cost, and therefore, or these particular system level metrics, excuse me, and then from there, how would we begin to move forward? And the idea from this approach is to understand, are there critical sets of interdependent materials properties that we need to go after in order to have a successful energy storage device? Are there materials design decisions that impact other aspects of the system? One example could be if I use a larger active species, say something that is polymeric or oligomeric, what that would allow me to do is to use a cheaper separator, maybe something that looks a little bit more like a coffee filter, because the large molecules aren't going to go through those larger pores of the coffee filter. However, pumping a polymer is really challenging. It's non-Newtonian. Sometimes it can have a yield stress. And so then all of a sudden my pumping costs go through the roof. So if I make a decision to use a polymer and say that it's going to help me with my membrane, I might affect something else in the system that might ultimately hurt me in the end. So we want to consider all of these things as early on as possible in the process. And then are there technical roadblocks that are obscured on the component level, say a material that's going to be very expensive or a supply chain that's going to be very challenging to meet? We want to try to take all of those into consideration as early as possible. And so our approach has been to say, well, what are the contributions to cost for redox flow battery? And so like a good chemical engineer, I can draw a control volume around my system and say, if I had a battery price and I said I wanted to hit, say, $100 per kilowatt hour, or you could put in whatever price you wanted to here, I'm going to need to have to pay for a reactor and everything that goes into the reactor. Oops. I'm going to need to pay for the electrolyte, and so that's going to be the solvent, the salt, and the active species for both sides. Excuse me. I'm going to have to pay for balance of plant. That's going to be pumps, tanks, heat exchangers. Apologies to everyone. I'm getting a little dry over here. So pumps, tanks, heat exchangers, controllers, sensors, all the other stuff that you need for the battery to work, but it doesn't actually store energy. And then to make it a price, you need to also think about additional costs like profit margin, overhead, labor, and depreciation. And so for this analysis, we're going to consider present and future state battery costs. I'm not going to consider installation. Installation is a big part of this, but as some folks know, installation is kind of a squishy thing. It really depends upon whether you're doing brownfield, greenfield, and what's already there. So I just want to think about the battery price for now. Excuse me again, everybody. And so what I'm showing you here is a little bit more detail as to how we try to do these calculations. These are relatively simplified equations. The top equation here shows the cost of the reactor, and you can see that it's going to be directly proportional to the cost of the materials that go into the reactor and directly proportional to the resistance of that reactor. So for me to operate efficiently, if I have a reactor that has higher resistance, I'm going to have to operate at a lower current density in order to maintain efficiency, which means I'm going to need a larger reactor. That's going to cost me more. It's also going to be inversely proportional to the square of potential. This comes back to what I mentioned earlier in terms of thinking about the cell voltage and how high cell voltage begins to help you. And it'll be inversely proportional to the efficiency. So if you have a low efficiency system, I'm going to need a relatively large reactor to provide the power that I need. Then on the lower side in the blue box is the cost of the electrolyte, where we see first outside of the parentheses the discharge energy. Again, you can see the cell potential in the denominator. This tells you that if I have a high cell voltage, I can store a lot of energy. Hopefully that makes sense for, say, things like lithium-ion batteries, store significantly more energy than alkaline batteries because they have a higher voltage. And then we need to add up the cost of the active materials, both on the positive and the negative side, the cost of the salt, and also the cost of the solvent. And these equations are a little bit complex. I've tried to put the citations for the papers where we work through all of the derivations, but if anybody can't get to these papers, certainly please do let me know. I'm happy to send them your way. In the case of the salt and solvent, if we're talking about aqueous systems, aqueous systems, that cost is going to be very minimal. It's going to be largely the cost of the active material. But if we want away from aqueous systems to say non-aqueous systems, then the cost of the electrolyte is going to become a larger fraction of this total fraction here. And so what I'm able to do with these types of analyses is hopefully develop materials design maps. And so I'm going to show you one such materials design map here. On the x-axis, I have area-specific resistance. Area-specific resistance, if you remember from the previous slide, is directly proportional to reactor cost. And on the y-axis, I have cell voltage, which impacts both reactor power and as well as electrolyte energy. So that I'll put on the y-axis. And what I'm going to show you here is a design map for batteries that are $100 per kilowatt hour. I'm going to focus on the battery cost, so no installation and no inverter. Those will matter in the ultimate cost of the system. And so what I can show you here these are contours of isomolality. That's moles per kilogram of electrolyte. And what you're looking at here in this green region that I'm showing you is the design space for, say, a non-aqueous redox flow battery. And this would be the region and the properties that you would need to make that battery under $100 per kilowatt hour. You'll notice some things that hopefully begin to make sense. First, I'll talk about the x-axis. So you can see that if the area-specific resistance gets higher and higher, we have a smaller and smaller design space to work with. And that should make sense. My reactor is getting increasingly expensive, and that becomes a more difficult thing to maintain and make $100 per kilowatt hour. As my reactor gets cheaper, though, it becomes a smaller and smaller fraction of my cost, and therefore I can afford to spend more on my electrolyte. So the design space begins to open up. You'll notice that also on the y-axis for cell voltage, you can see if I have lower cell voltages, I need to have really high concentrations of active species. And the reason is because my electrolyte, my salts and my solvent are also going to be expensive. But as I get to higher cell voltages, I can get to less and less concentrations of my active species because I'm having more and more energy stored because of my higher cell voltage. We can then look at a similar type design map for aqueous type systems, and we can sort of see here that aqueous systems tend to have lower cell voltages, say typically 1.5 volts, but it can be up to maybe 2 volts, say in the case of a lead acid battery. But we can see also that there's a design space that exists, but it's a little bit smaller. And we'll notice that we don't have quite the same sensitivities. We're less sensitive to area-specific resistance of my reactor, and we are less sensitive to the concentration, and that has to do with the fact that the electrolyte is cheap. We can take these kind of design maps and then come up with maybe some targets that we would like to get after. And so what I'm showing you here on the right-hand side of the screen now is key performance metrics for, say, a 5-hour discharge redox flow battery. So we want to have cheap active materials, less than $7 per kilogram. We want to have lower molecular weights. For aqueous type systems, we'd like to have high cell voltages and low area-specific resistances. And for cell voltages, active species concentrations, we'd like to have, for non-aqueous systems, higher active species concentrations. We'd like to have cell voltages that are quite high. We'd like to have area-specific resistances that are low. And we'd like to minimize our salt cost factors. And I'm being told I need to speed up here. I apologize. I'll go a little bit more quickly towards the end. But what hopefully you can take out of this is that while there's a broader design space for non-aqueous redox flow batteries, and so an academic like myself finds this to be very interesting, there's significantly more technical risk associated with this type of approach as compared to aqueous systems that are significantly more advanced. There's already stuff in the market. And so in the near term, aqueous systems look quite promising, but in the long term, maybe non-aqueous has a role to play. And so moving forward, I think if we're thinking about next generation redox flow batteries, we need to think about inexpensive chemistries. We want to think about materials that are widely available and can potentially be used on a broad scale. And so one example of this could be sulfur or polysulfides. We pull sulfur up anytime we pull oil and gas out of the ground. And so there's a tremendous opportunity to be able to use something like sulfur in a redox flow battery. Even people are looking at it, say lithium sulfur batteries for enclosed type storage. There's no free lunch, as I mentioned earlier. Sulfur is a very difficult system to work with. It's got a lot of challenges, but if it's going to be this cheap, it might be a challenge worth going after. Another approach that people are thinking about is tailored organic active species. So using organic materials, they could be derived from petrochemicals or from other sources. The nice aspects of organics is that you have many tailorable properties based upon molecular functionalization and tweaks of organic chemistry. We've looked at this relatively extensively. I can tell you it's a difficult space to work in, I've found, but I'm lucky to have a number of very strong chemistry partners. As a chemical engineer, it means I'm an okay chemist, but they're the organic chemists of the world. There are many different things that we can look at and many different molecules that exist that people have looked at for previous applications that may be applicable for large-scale energy storage. The question, of course, with organics is, are they cheap? And of course, with any good answer, it depends. It depends what you're trying to do. And so I'm giving you one example of an organic that people are beginning to look at for energy storage. This is anthraquinone disulfonic acid. You can pull it out. As we know, we make anthraquinone, and we use anthraquinone as a catalyst to make hydrogen peroxide on a large scale. And so the transformation from anthracene, which is derived from crude tar, to anthraquinone is a relatively well-studied process. And the next step to make it anthraquinone disulfonic acid is a sulfonation process. You can make a relatively simple process flow diagram to begin to look into this. So starting from anthracene and saying, can I go from anthracene oxidized to anthraquinone, and then sulfonate it to go then to AQDS. And then we can look at, say, well, what would the costs need to be, or how would the cost vary as a function of production? And that gives us some sense as to how much we think that this material might cost. Again, remember, this is a relatively coarse approximation, but you can see these materials have the potential to get to relatively low costs relatively quickly, below $5 per kilogram. Of course, it remains to be seen when we build it out how cheap they can get, but this gives you a sense that organics can be relatively cheap if the right materials are selected. And so finally, I want to finish up with a couple of grand challenges. The first is guided synthesis of matter with precise properties. And so how can we accelerate invention, discovery, and synthesis of molecules, materials, and interfaces that have targeted property sets? And there's been tremendous advances over the previous years focused on QSPR, so quantitative structure property relationships, or the use of computational methods to design and screen for materials. So think the materials genome, think the electrolyte genome, things of that nature, that allows us to screen broad design spaces and begin to identify new redox molecules that might take us years and years to discover in the lab through classical trial and error. The challenge with these types of approaches right now are the outcomes universally applicable, or are they dependent upon local factors? So for example, if I find a molecule that works, say in acetonitrile as a solvent, would that molecule also work in water? How much do those properties transfer from one system to another? So that would be advances in discovery and the rate of discovery and the development of new materials. The second is coordinated design of molecules and membranes. I mentioned earlier that one of the challenges with current redox flow batteries is the fact that we use fluorinated membranes, and the fact that many of those fluorinated membranes are not 100% selective to the active species, so you're always going to have intermixing. This becomes a challenge when you want to get away from symmetric chemistries, such as vanadium, and to move to asymmetric chemistries where we have two different species on either side of the membrane. There are other approaches that people are looking at, thinking about materials that might be operating, starting from small molecules and working their way up to larger redox active colloids, large nanoparticles that are suspended in solution. And this gives us new options in terms of potentially cheaper membranes. But in doing that, you give up and have issues with things like transport in the battery, redox kinetics, solubility, and cost. And so being able to identify and balance what is the sweet spot across this range of materials is a really big question going forward. And how do we then think about that kind of design and coordinating it with the membranes that we can use? And the final point I want to make here is quantifying and mitigating decay mechanisms. I mentioned to you that vanadium is a really robust system because vanadium doesn't decay into anything else. It can precipitate and we can redissolve it, but vanadium is not going to turn into another species. Organics will, and organics can break down and decay over time. And so how would you deal with that, a system that has a finite lifetime? Would you need to replace the electrolytes? Would you need to strain out some of the spent material and introduce new material as well? All of these are open questions. But more generally for flow batteries, one of the things we mentioned earlier is that these batteries are expected to be working for decades, right? And so how would you know that the battery is going to work for decades? How would you be able to predict that early on? Would you need to run it for decades to know that? Or are there methods to accelerate our understanding as to how these batteries would decay, and what sparing strategies or what new approaches we would take to increase the lifetime, such that you would have an installation that you say would last for 20 years and you'd have some confidence that it would last for that period of time. And so being able to predict lifetime without necessarily having to run for that lifetime is an important next step here. And so this is my last slide. And maybe in conclusion, what I hope you've been able to take away from this is that redox flow batteries are promising, but a somewhat nascent technology. Early stage techno-economic modeling can help us inform research directions and highlight technical bottlenecks, hopefully then bringing more people into this field and identifying new pathways forward. These flow batteries are promising for long duration energy storage if inexpensive electrolyte chemicals can be found, and if we can reduce the cost of bound to plant designs. And in the discovery of new materials or the advancement of new materials, process-based cost modeling may help us to identify those cost effectiveness of these new materials before we advance too far and spend too much capital before we know if it's going to work or not. So I want to thank you for your attention. Apologies for the slight delays as I dried out during this talk, and I'm happy to take whatever questions folks may have. But if you have questions that you don't get answered, certainly please feel free to reach out to me via email. It's my last name at mit.edu. Thank you.
Thank you, Fick. That was comprehensive and really interesting. I have 200 questions that I will draft and send to you by your email address.
Oh my, okay.
.edu. And I hope others will take him up on the opportunity to do the same. Let me just ask a couple, because it's such an important technology type, I think, coming down the path that people have questions. And I think what you've described is a very complex engineering problem. And you even talked about the techno-economic approach to understanding the variables and cost drivers. And I think probably the most interesting of the questions that flew by on the screen here was, how do you know you're right? How do you know that engineering cost analysis is going to be reflected in reality?
That's a really difficult question. And as with any prediction, it's very difficult to know if you're right or not. The ways you go about it is you start to bring that prediction to people who are actually working in the industry. And so a lot of that analysis I couldn't do if I was sitting in my office with my students trying to work up these numbers. The math is relatively simple to put together, but the challenge is how much does stuff cost, right? I buy things from Sigma and other vendors like that, and so that's not reflective of commodity scale pricing. And so what we try to do wherever we can is to partner or to engage with people who are active in the area, not just people who are making flow batteries, but people who are also doing chemical manufacturing, people who are also doing component development. They won't give you the actual numbers that they have, but they'll tell you if you're in the right ballpark or not. And so the numbers which I've shown, I think the goal is to try to understand trade-offs, right? So what are the trade-offs and what might success look like? But the idea is for these kind of tools that people who have more information or people who would like to put in their own numbers and see where things pop out are able to use those kind of tools. And if they put those forth, then they can come up and draw their own conclusions and identify their own pathways forward. I will say that, cost numbers are always very sticky, especially predictions. And if I could predict the future, then I would probably be very rich, and I'm not. So, predicting the future is always a risky thing.
Well, no, you've just got tenure, so you can waste some time. And do you have an entrepreneurial future, or is this the wrong technology, or is it too early?
Do I have an entrepreneurial future, or does this technology? I think the technology does.
Part of it.
I think the technology does, and I'm trying to help out in any way that I can. I don't know that I'm great at business ventures, but we try to provide support. We try to, train students and train people to think in this area, to provide talent to advance the different technologies. One of the things I definitely want to key off that Professor Sadoway said is that it's not one technology versus another. There are ranges of different technologies. And so if people are well trained in the area, I think that we can advance new approaches very well. And so that's my goal, to hopefully just bring more attention to the area, more good scientists, more interested folks, and help us move forward more quickly.
Well, Fick, we've run out of time, but I'd like to
no, I'm
thank
sorry.
you on my behalf and behalf of everyone who's joined us. It's really an interesting session, and I'm sure you're going to get a lot of emails.
Okay. Apologies to those folks who had Q&A. I didn't mean to go so long. I wanted to hear from you. I apologize.
You answered many of the questions.
Oh,
Thank
great.
you.